Welcome everyone to tonight's webinar. It's part of the VCE Specialist Mathematics series, and this evening we'll be focusing on lines and planes in 3D. These include things like cross product, that's new to the VCE Specialist Maths course, intersecting and skew lines 2 and 3, intersecting planes, vectors, parametric and Cartesian form, systems of equations, parametric and Cartesian equation of a plane. There's a lot to get through. So I'll introduce tonight's speaker, and that is Bojana. Bojana's taught specialist maths at Wesley College in Melbourne. She also teaches IB. She's been a VCAA assessor in specialist mathematics, so I'm sure she's got a few clues and insights that she can share with us during the presentation. She's also presented at all sorts of conferences, and I'm glad we've got her on board to go through this topic. So, are you ready to share your screen, Bojana?
Thank you. Yes, if you make me a presenter, please.
We can see your screen now.
Thank you, Peter.
It's all yours.
So, yes, as Peter said, there is specialist mathematics is changing quite significantly, and big changes are in vectors. So we had cross product of two vectors, including the determinant form. We don't know exactly what applications, but we assume area of the triangle, parallelogram, and normal vector to the plane. Vector and Cartesian equations, this first one stays as it was, but we have a vector equation of a straight line given the position of 2 points or equivalent information in both 2 and 3 dimensions. So vector equation, parametric equation, Cartesian, vector cross product normal to a plane, parametric Cartesian equations of a plane. We don't have any more detailed information, so it's a bit of a guess game what we'll be teaching. But yes, these are the main things we usually do with the cross product. So vector product and methods determining vector equations of lines and planes, system of equations, and formulate problems which require solutions with systems of linear equations. TI-nspire is a wonderful tool because we can draw lines and we can draw planes in 3 dimensions. But we'll start with a cross product, and I'll talk about the applications of cross product. So let's go to our TI-nspire. So let's say that we wish to find the cross product of 2 vectors. So let's do a simple thing. My first vector, I will call it A, and we use the square brackets, 1 minus 2, 3. Let's say that my second vector, let's say position vector OB, and again, I defined it using the square brackets, 2 minus 3, 1. So I have those 2 vectors defined. Similarly, as with the dot product, we use the matrix and vector application, and we have here the cross product. And because I defined those vectors, so I can say the cross product of AB is 7, 5, and 1. So that's a simple application. We can play with what happens if I find the cross product of B and A, and we can clearly see that we have the change in the direction. So that can be set up nicely in a notes page. So then, of course, it allows us to change A, B, and play with those vectors. We can also define our unit vectors, I, J, and K, and find the cross products I, J. which gives us the k unit vector. Cross product of jk gives us the I unit vector. Cross product of ik gives us minus j vector and so on. And of course, cross product of ii or any cross product of jj will be 0 because those vectors are parallel. So the cross product is another feature of the TI-nspire calculator, and we can easily use it like we did with the dot product. So here is a picture how we use the right hand screw for our Kij, and also a nice picture for the students going this way, it's positive, going this way is negative. We can also, in the notes page, have any vector in general, and then we'll get the formula for the cross product, which links to the determinant if students will be doing it by hand. So let's think about this problem. Find a unit vector perpendicular to both vectors. So we think what is happening here. We're given two vectors and we want the vector which is perpendicular to those two vectors, but we also want it to be a unit vector. So likewise, I will get a new calculator screen and I will say my vector u was 4, 3, 2, and then my vector v is 8, 3, 3. So if I want the vector perpendicular to both, of course, it is the cross product. I find typing it is faster than trying to go through all the screens. So I have u and v. So this is the cross product, but of course, this vector is not a unit vector. So if you remember, metric vector norm gives us unit vector first, then norm. So we go matrix and vector and unit vector. So we take this vector and this is our unit vector, which is perpendicular to two given vectors. How can we check that it is actually length 1? Of course it is, because that's how we set it up, but norm gives us the length of the vector, and it shows that the length of this vector is 1. So these are just some basic applications of the cross product, unit vector, norm, and similar concepts. So the cross product has an application to find the area of a parallelogram or area of triangle. By definition, it is AB sine of the angle, so it nicely joins links to the area of the triangle, which is half. Parallelogram is just the magnitude of the cross product. So have another example here. Find the area of the triangle OAB. O is the origin, and we have A has position vector I minus j, B has position vector 3i plus 4j minus 6k. So let's get another application. And oops, we'll better do new problem because I already used A. So let's do new problem and calculator. Then my A is not used. I can use it again. So I do vector A, which was 1, -1, and this one was just in ij plane, and vector B. So I repeat a few of those just to show how it works. 3, 4, -6. And I find cross product again of A and B. Now I find the magnitude of the cross product. That gives the area of the parallelogram. And if I divide this by 2, that gives me the area of the triangle. So that's one of the applications of the cross product, finding the area of triangle as by this picture. Let's have a look, a slightly different question. Find the area of the parallelogram ABCD, where A, B, D have position vectors. So we have position vectors like this. So I drew this nice little diagram. We are given position vector A, position vector B, position vector C. So again, we can use the calculator to simplify our calculations. So I do insert new problem again. So in the calculator screen, and I will define my position vectors A, B, and C, which was 2, 1, and -1, and B had position vector B was 6, 4, -3, and C square bracket 14, 7, and -6. So these were the position vectors, but if I wish to find the area of the parallelogram, I need vector BABC cross product. So what I can say now that my vector BA, and the calculator will do it nicely for us, is vector A minus B. And I need vector BC, and that is good for the students if they do it on a calculator, because they will not make a mistake. So BC is equal to C minus A. So now I have those two vectors, and I just find the cross product of, and you probably know that all the variables are there. So I can go BA and recall BC. And now I find norm, the magnitude of this vector, and that gives me the area of the parallelogram as requested. So these are the main applications for the cross product. Now, the next thing I would like to show is graphing the straight lines and planes in 3 dimensions. So I will close this one and close this one. I will open a new document and we'll go graphs. So if we want to draw in 3 dimensions, we go menu, view, and it's something which is called 3D graphing. So we can see now that the box with 3 axes appears. Now I start by drawing straight lines. So again, if we look at 3D graph entry, I can have a function, which is what it started with, and we draw planes using function. But if I wish to draw a straight line, I will use the parametric entry. So this is a parametric entry for the straight line. And let's draw one of those lines. So let's say that my parametric equation was 1 plus 3t and 2 plus 4t and 3 plus 5t. And I can see a tiny bit of a straight line here. I could change the color because that helps a bit. Sometimes you have to do it twice. Line color, red. Didn't want to do it with, yes, it's red, but we can only see a tiny bit of that line. So how can we overcome that? We need to change the parameters. So if I go back here and I press 3 dots, so you see my parameter was only 0 to 2 pi. Let's say if I go minus 20 pi to 20 pi, and I go back to here, now I can see much more of this straight line. We have a few other things. If we go to actions, I can do our auto rotation. So the calculator will rotate the box and I can see this line in 3 dimensions. Escape stops it. I can also rotate by just dragging the box. So this is how we draw a straight line in 3 dimensions. If we wish to draw a plane in 3 dimensions, so let's do a new problem. And again, graphs. Similarly, we go to menu and we need to get 3D graphing. So equation of a plane in 3 dimension, Cartesian equation is ax plus by plus cz equals d. Here we need to make z the subject. So let's say I want to draw the plane y minus 2x. And I can see this is my plane y minus 2x. I can rotate it and I can see how the plane looks like. I could draw another plane here. Let's say I will do negative x plus 3y plus 2. And I can see another plane, and if I rotate, I can see how nicely those two planes intersect in a line. How could we find the equation of the line of intersection? We simply use linear solve on the calculator. So if I get the calculator screen, and I go menu algebra, solve system of equations. I have 2 equations, but I have 3 variables. And of course, the calculator will do it for us. I have 2 planes, but they are in 3 dimensions. So my first one was z, or second one was 2 minus x plus 3y, and the other one was z equals y minus 2x. Wow, that looks quite funny. So what is the meaning here? The calculator gives us the parametric equations of a straight line. How does that translate? That means that x is minus 2t minus 2 on 5, that y is t minus 4 on 5, and z equals t. So if I now try to sketch this straight line going back to our plane, I should check that actually those 2 planes intersect in the line. So I had the entry which was function entry, so I need to go back and change it to parametric entry, and I will use a fraction. So we had minus 2t -2 on 5. And y was, again, if I use the fraction, that's easier, t minus 4 over 5, and z was t. Again, I might not see too much here, so let's try to play a bit with the parameters. So maybe do minus 40 pi. Again, it's a bit of a trial and error. 40 pi. And now it's a bit tricky to see this line, so you need to go here, and now I try to change the color, and I will say make it yellow. And now didn't do yellow, did blue again, line, color, yellow. Doesn't want to work yellow for me, but doesn't matter, it's blue, and we can see this is the line of intersection between those two planes. We can draw a special plane, like if I enter another graphs and menu, view, 3D graphing. Let's say that I have the plane which is just the horizontal plane, and that was z was equal to 2. We could do parallel planes as well. So let's try this. I just need to get my equations. So again, get another set of graphs and menu, view, 3D graphing. So I chose one equation being 2x plus 3y minus 5 over 4. And then if I do it again, the parallel plane, which would have the same normal vector, just the scalar multiple, 6y minus 2 over 8. And now if I rotate, I can see that those two planes are parallel. The other thing you can change is you can change the box. Let's see, those planes are pretty close together, but if you do auto rotation, it does show that the planes are parallel. The other way, the other thing we can change, and you can try to play with that a bit. Oh, my mouse is dead. I have to use the computer mouse. We can also change the range settings, or you could shrink the box, multiply the box, and so on, or just do the range settings by hand. So if I go, let's say, minus 20 to 20, minus 20, sometimes it helps with different situations, so that's something to 20. So they will be even closer together because I made the box really big. So if I go Control Z, I can go back to the same thing we had there. So that's how the calculator helps us drawing the planes and lines in 3 dimensions. So I covered the cross product. We did some of those applications. Graphing, again, entry parametric for lines in 3 dimensions, and you can use parameter t or another parameter u, it will work, and changing parameters if the line is too short, and changing color as well. So let's say we have 2 lines and we wish to find the point of intersection. So these are 2 lines given in vector form. which of course we can change it to a parametric form. So if we wish to find the point of intersection, all we need to do is to change each to Cartesian form. So 1 plus 3 I called alpha A, 2 plus 4A, and equal x coordinates, equal y coordinates, and equal z coordinates. And the calculator will give us alpha and mu. And once we know alpha and mu, substitute to any to get the point of intersection. So the two lines intersect in the point, and you can draw them and rotate and locate this point. Of course, you can't really find the intersection easily, but we can see what it is. So these lines in three-dimensional lines do intersect, and there is a few other screens how we draw it. So here we have the Cartesian equation of the plane, and we have find the equation of line of intersection between those two lines. Give your answer in parametric form. So similarly as we did before, we can draw it and see what happens, or we do linear solve. Again, we need to remember we have three variables but two equations because these are two planes. And now these two planes, as we can see, intersect in a straight line given by this, which we showed before. That's how we translate this funny entry on the TI-nspire. And of course, if you do it a few times, your C1 will change to C2 and so on. So Z is T, Y is that, and X is that. And these are the parametric equations of a straight line. We looked at vector equation, and also we have the Cartesian equation. If we make T the subject and equal them, then this is the third form, which is the parametric form. And we did this nice intersection there. Now, angle between the line and the plane, this one is a bit tricky, because if we look at the normal vector to the plane and direction vector of the line, and we find the angle between those two, then we'll not be having the angle which is there. So we can do either arc cos, inverse cos, and 90 minus, or we can do arc sine. So those things will both work. So if we look at our normal vector to the plane, this is given in another form again, the plane r dot. So 3, 4, 2 is the normal vector to the plane, and this is the direction vector of the straight line. So of course, on a calculator, we can do this, either cos minus 1 and 90 minus, or sine minus 1 will result in the same idea. Angle between two planes is pretty straightforward, which is just the angle between normal vectors. So 4, 4 minus 7, 7 minus 4, and 4. We define those two vectors. We find cos minus 1 using dot product and norms. And if we want the acute angle and using the normal vectors gives us obtuse angle, we go 180 minus. So these are some of a few applications of lines and planes in 3 dimensions. Now, line and plane intersection. So if I have the line given in vector form and my plane with the normal vector, so what we need to do, we need to substitute the thing to the equation and solve, and that gives us the point of intersection. So a few other ideas. Now, how can we find, it mentioned Cartesian equation, can get rid of them, of a plane through 3 given points or line through 2 points. So if I have 3 given points and I want to find the Cartesian equation of the plane, we need to find the normal vector using any 2 vectors. So if I say my position vectors A, B, and C are, we did it already, I find A, B, and AC, and I find the cross product. So that gives me the normal vector. So I would say the equation of the plane is minus 6y plus z equals d. To find d, substitute any of the points. And that's how we can easily find the Cartesian equation of a plane through 3 given points. Shortest distance from the point to the line, again, I'm not sure whether that questions like that will appear, but of course, that's one of the applications. So if we imagine our straight line, and we can take any generic point on the straight line given in parametric form, and we have A. So clearly, if we find AB and dot direction vector of our straight line and equate it to 0, we'll find the parameter. Once we have the parameter, we can find the shortest distance. So again, this time we'll do AB by subtracting the general form, and we find dot product AB. And if we solve, we get the parameter minus 4 on 9. Then we can find the length of the vector given this, and the norm of this vector will give us the shortest distance. So there's a few applications which could happen. Now, this is the investigation which will be in one of the files for the students, and I provided the solutions. So it starts with consider the 2 lines and the line L1 and L2, and they are given in parametric forms. Show that these 2 lines do not intersect. Of course, by hand, students equate the first 2 x's and y's, find the parameter, substitute to the third, show it is the contradiction. But of course, the calculator will nicely tell us no solution found. So skew lines is quite a difficult concept in 3 dimensions. They are not parallel, but they do not intersect. I usually look at the room and show them 2 lines, like one edge of the room and the other edge, to explain what the skew lines are. So this first part. The second part is find the equation of the plane containing line 2, which is parallel to lane 1. So the plane will have line 2 and will be parallel to L1. So let's say that the Cartesian equation of the plane is ax plus by plus c plus d. So we have 4 unknowns. So we need to come up with 4 equations. So normal vector of the plane is A, B, and C. And normal vector of the plane is perpendicular to direction vectors of both lines. So that will give us 2 equations. Because we have 4 unknowns, we need 2 more equations. But we know that the plane contains L2. So we can select any 2 points in this plane to form 2 more equations. So easy points, if parameter m is 0, the point is 2, 0, 1, parameter is 1, of course we can use any. And now we form 4 equations. So the first 2 are using the dot products, and those other 2 are using our points in the plane. And again, we get this funny answer. So how do we translate this into the equation of the plane? We can just copy 5 on 9x plus 7 on 9y minus 1 on 9z is 1. To make it a bit nicer, we multiply everything by 9, and this is the equation of the plane. So if I go back to the calculator and skew lines, so I have the picture here, actually that was the picture which I had. So this is what I drew. So the blue line is the line which lies in the plane, and the red line is the line which actually is a skew line to the plane. So that confirms that our thing works. So if I do auto rotation in various positions, there is this blue line and blue plane, so it's not that well visible. So it's probably actually better to rotate it to see that this one of the lines lies there and the other one is a skew line. So that is this part of the investigation. So we got the line and we can try to sketch it on a calculator showing that the blue line is in the plane and the red line is parallel to this line. Now, the next part in this investigation, I said, what if we want to find the distance from the point on the line or the distance between those two lines? So we can take any point on this line and find the distance from the Cartesian plane. I don't know whether this formula will be given, but that's quite popular formula, finding the distance from the point to the plane, absolute value, and here we substitute the point, and A, B, C, and D are the Cartesian equation of the plane. But the idea carries on, given that V1 and V2 are direction vectors for our L1 and L2, find the vector product. Then taking a general point A on L1 and general point B on L2, find vector AB. Find points AB such that AB is parallel to V1, V2, and find the length IB and see what do we get. So we do V1 and V2 and cross product as asked here. And then I find those two direction general points on the lines L1 and L2, and I find L2 minus L1, and I want that to be parallel. Sorry, I have to go back. So all this is there. I think it is a nice investigation. So we solve, find K, T, and M, and we find the normal vector, which the magnitude of this vector, which actually gives us the same result as we did before. There is one other investigation which also is on the website for Texas Instruments Australia, where we have system of linear equations and there are special forming some sequences, so that combines, that could be done even in year 11, combines nicely simultaneous equations, solving them in two-dimensional space and trying to come up with the envelope and doing some algebraic forming the conjecture and doing some proofs. So we also have, I also we also, in the files, there will be the student worksheets with some questions and provided solutions, so which can be used in class like a little test if you wish, and those two investigations. I might pass to Peter now because Peter did a nice visual representation of the cross product. So thank you for listening. And Peter, if you want to share your screen and show your nice cross product in 3 dimensions,
I can do that for you, Bojana. That was wonderful. Lots of good challenging questions for people to try there. Yes. Before this session, Bojana and I were talking about some of the things that need to be covered, and there's a lot that needs to be covered. I mentioned the other week that I like the stuff that Grant Sanderson has done on linear algebra. I'd still recommend that to help students understand some of the stuff we're doing here. He's got a beautiful explanation of linear dependence and independence, which is in the course, and how it relates to 3D and graphing and all of those sorts of things and planes. So it fits nicely into what we're doing. I believe, if my memory serves me correctly, there's also a neat little activity on our senior maths curriculum section. Let's have a look if we can find it in here. There's one on, it must be under algebra, I think. Just bear with me. Functions graph algebra, here we go. 3D equations. So this one you can download, it's already up there. And the idea of this one is for students to practice solving 3D equations. I think it'll be a useful task for them to do. So I'm just going to open up the TI-nspire activity file so you'll see what that looks like. Waiting. There it is. So it says use a slider to select the equation set that you want to solve, so we can choose between different sets of equations. And then once we've chosen our set of equations, we navigate onto page 1.2, and it looks a bit messy, but you can toggle some of the graphs on and off. So we see that equation 1 and 2, they intersect along a line. Equations 1 and 3 intersect along a line, and equations 2 and 3 would intersect. So it's looking at the different ways that you can display that information. And then it says, okay, let's start with equations 1 and 2 and decide how we're going to eliminate one of the variables. So we can multiply equation 1 by 3 or 2 or something like that. And you can see I've managed to eliminate x. If I want to eliminate z, for example, when I'm looking at these, I might say, well, if I'm subtracting them, I might change that to add them. I'll add equation 1, I'll have one lot of that, and 2 lots of equation 2, and I've eliminated the z. So that gives me an equation. Now we can then have a look at what does equation 1 and 2 look like, and then we see our line that we're getting from here, this 4x minus y, that one there. So that's one that you can download, but the one that Bojana was referring to was this little one here, which I've done on cross product. There's a lot happening on this screen here, but I've got the plane drawn in, so let me just hide the plane for a moment. And we've got some vectors or some lines happening here, and we can wiggle them around a little bit. So they're vectors that I've got defined in the notes application all the way back up here. So vector A has got AI plus, that should say BJ. No, that's right. No, AJ, AK, and BI, BJ, and BK. So they're the values I've got in there, and you can see the vector there, and there's the other one. And it's automatically calculating the cross product. So what? Let's have a look in here. The cross product, that's that line there. I think it's important that students understand what that line is actually doing. As Bojana said, it's perpendicular to the plane. So as I move these points around, we can see it kind of moves, but it's a little bit ugly as it stands. So I could try and rotate it. I put in the chat there that you can press A to do an auto rotation. There's still lots of lines just kind of spinning around. So I don't think students are necessarily going to see it from there. I think on some angles you might get an idea of what's happening. So I'll just press escape there, and that's where it's handy to put the plane in. So now we can see that the plane is perpendicular to that cross product. So as I flip it around, I don't think it's too bad. Now, if you only want it as a teaching tool, if you change your software across to computer view, you'll see that the image that it gives you is a lot better. That's because the other space is trying to, I guess, portray exactly what the calculator is showing. Now, the other cool thing about this, the two vectors you can see sitting on that plane, that green one and what looks like a blue vector. I thought I had it red, but never mind. Blue and green vector there. If I just multiply them by some scalar product or some scalar, you can see all I'm doing is shortening it or lengthening that vector. Now, if I wanted to get to any point by combining those two vectors, any one of those points would be on the plane. That's the whole idea of those two vectors, is if we combine them, they'll create a point on that plane. No matter what I multiply them by, I should be able to. I didn't do some negatives. Let's see what happens. I'm going to change this. I'm going to change the settings so that we can have some negative values. Let's get a -5. Let's see if we can get it to, oh, there we go. It's reversed the direction, so that's nice. We'll do the same to this one. So you can see it's easy to change the file up a little bit. So we can point them back in the opposite direction. And it's interesting because our cross product is not changing when we multiply it by a scalar, and nor should it, because we've still got the same plane. So our cross product is still going to be off in the same direction. So it's a nice little visual, I think, just to demonstrate what's going on. The other thing that's really cool about this is that we can talk about linear dependence and independence as if I put a third vector in there and that vector was on this plane, then we would say that it's effectively redundant because we could have used the two existing vectors to reach any point on that plane. So if the third vector sits somewhere on that bluey, purpley colored plane, then we would say that those vectors are linearly dependent. So it needs to be protruding off that plane in some way so that it would avoid being linearly dependent. So that's that particular activity. The other thing I thought was useful, because I noticed in the study design, Bojana, it references the cross product in relation to, did it say the determinant of the matrices?
Yes, but yes, of course, we can't cover everything, but I think it's more using this IJK, one vector, another vector, how to use the form for getting by hand, yes.
Yeah,
but not
so
calculate.
just while you're talking, I threw this together, so hopefully it creates enough of a visual for people to know what they mean by that, because there's a lot of stuff that's been included. And it's interesting. Oh, I'll show you something else too when I go back to the file. So here we've got two vectors, and if we kind of blend them together, and the top row is our I, J, and K. Did you like that little animation, did you? And we want to do the cross product. So if I want the first component of the cross product, I just cover up that column there. And then we find the determinant of, if you like, this little sub-matrix here, this one here. We find the determinant of it, and that gives us our coefficient in the I direction. So -2 by 2 is -4, minus 1 is +1, so -3, there's our first term. Then we subtract the next term, so we cover up the J direction, we work out the determinant of this, which is 2 by 2 is 4, -3 is 1. We subtract that to get -1. And then, of course, we can figure out what the last one is. We cover up the K direction. We define or determine or calculate the determinant there. So therefore, we've got -2 minus -6. So that makes it what, 4. So there's our cross product.
Nice.
I suspect that's what it's referring to for that.
No, yeah, it is. But
yeah.
it's
So
what we do by hand.
Yeah, and so the last point I want to make, so there's those two vectors that I had there. I've done them as column vectors. I noticed the study design refers to column vectors. I'm with you. I'd rather write IJK going across the page rather than this, but it certainly does seem to refer to it. So I think we need to make sure students are fluent in vertical and horizontal representations of vectors. But you'll see here, it doesn't matter. The calculator doesn't care whether those vectors are written vertically or horizontally. It's fine. So we'll get our answer -3, -1, 4. So I think we've just about got a wrap up there, Bojana.
Thank you, Peter, and thank you everyone for listening.
Yeah, I thought it was fantastic. And look, those activities, Bojana's notes and everything will be up on our website very soon. That question sheet she put together with all the solutions, so that'll be good practice for everyone. And I'm sure the textbooks will have lots of good content in there as well. All right, well, thanks everyone for joining us, and we'll catch you next time.